Hey everyone, and welcome back to the channel. Today we're going to be tackling something that might seem a bit like magic at first, but I promise it's pure science. We're going to be talking about electric current.
You know, it really is fascinating how electricity powers literally our entire world. Yet most people don't really even stop to think about how it actually works.
So let's shed some light on electric current. What is it exactly?
Well, at its core, electric current is simply the flow of charged particles. So you can imagine it kind of like a river, you know? But instead of water molecules rushing downstream, you have these tiny little particles carrying an electric charge that are moving along a set path.
Okay, so like a microscopic highway full of tiny electric cars.
Exactly. And the most common type of charged particle hitching a ride on this highway is the electron. You know those negatively charged particles we all learned about back in science class?
Ugh, electrons, our old friends. But hold on, isn't it a bit more complicated than just electrons flowing around? I've heard of things like ions and electrolytes and things like that.
You're absolutely right. While electrons are definitely the usual suspects in things like metal wires and other materials, the charge carriers can actually be ions. Now, ions are basically just atoms that have either gained or lost a few electrons, which gives them a positive or negative charge. And you find these ions doing their thing in things like batteries, where the medium that they move through is called an electrolyte.
Okay, starting to get the picture here. But if I'm being honest, trying to visualize these tiny particles zipping through wires, it still kind of makes my head spin a little bit.
I hear ya. It's definitely abstract. Think of it this way. Imagine a crowded room where everyone is just kind of milling about randomly. That's kind of like the electrons in a wire with no current. But the moment everyone starts moving in the same direction, like a flash mob suddenly breaking into a coordinated dance, boom, you've got electric current.
Now that's an image I can get behind. A flash mob of electrons all moving to the same beat. But isn't there some kind of scientific quirk about the direction of this flow? Something about conventional current?
Ah, yes, that's right. You see, back in the day, before scientists really fully understood what was happening at that atomic level, they decided that current flows from positive to negative, and this is what we call conventional current.
But I thought it was the negatively charged electrons that are actually doing the moving.
Exactly. It's a little ironic, right? Even though we now know that it's usually the electrons flowing from negative to positive, we still stick with that original convention of positive to negative.
So it's like we're looking at the current's traffic pattern from the wrong side of the road.
Exactly. Think of it as a historical quirk. It doesn't change how electricity actually works in practice. It's just the way that we represent it in diagrams and equations. It's like choosing which side of the road to drive on. It doesn't change your destination, just the agreed upon rules of the road.
Gotcha. So we've got these charged particles, could be electrons, could be ions, flowing along their designated paths. And we think about the current going from positive to negative, even though the electrons are often doing the opposite.
Got it. But I'm guessing the story of electric current doesn't end there, right?
Oh, you are so right about that. We've just scratched the surface. Electric current isn't just a one-size-fits-all phenomenon. There are actually different types of current, each with its own unique personality, you could say.
Oh, different personalities. Now I'm really intrigued. Sounds like we've got a lot more to unpack here. Stick with us, folks, as we delve into the fascinating world of the different types of electric current.
Welcome back, everyone. Before the break, we were delving into the world of electric current, that flow of charged particles.
And we learned that while it's usually electrons making the journey, sometimes it's those charged travelers we call ions instead.
Right, and remember, we still think about the current flowing from positive to negative, even though the electrons are actually moving the opposite direction. Yeah, all thanks to that historical convention. It's like trying to teach an old dog new tricks. But you mentioned that there were different types of electric current, each with its own personality. I'm ready to meet these characters.
All right, let's bring them on stage. The two most common types that you'll encounter are direct current, or DC for short, and alternating current, also known as AC.
Okay, those names definitely ring a bell. I know I've seen AC/DC on everything from power adapters to, well, rock bands. But what makes them different?
Well, with direct current, the flow of charge is constant and in a single direction. So it's kind of like a one-way street for those charged particles, always heading towards the same destination. Think of the steady current that flows from a battery.
So batteries are all about that DC life, huh? What about AC then? What's its deal?
AC is more like a busy two-way street where the flow of charge is constantly changing direction, switching back and forth rapidly. It's a bit less predictable, but incredibly versatile.
Like a highway, with reversible lanes. So is that what's happening in the electricity that powers our homes?
You got it. Most of the power we use in our everyday lives comes in the form of AC.
Interesting. So we've got these two distinct types of current, each with their own flow pattern. But why bother with two? Wouldn't it be simpler to just stick with one?
Now that's a question that takes us back in time to a fascinating historical rivalry known as the War of Currents. Imagine it. The late 19th century, the dawn of the electric age, and these two titans of science are locked in this battle over which system would illuminate the world.
A war over currents. Sounds intense. Who were the contenders in this epic showdown?
On one side, you have Thomas Edison, a staunch advocate for DC power. He believed it was safer and simpler to manage. And then on the other side, you had Nikola Tesla, a visionary genius who championed AC power. Tesla saw the potential of AC for long-distance transmission, something that was far more challenging to do with DC.
Wow, a real clash of the titans. I never knew there was so much drama behind something as fundamental as electricity. But I'm guessing since we mostly use AC today, Tesla won the battle.
You're right, Tesla's vision ultimately prevailed. See, AC's ability to be easily transformed to higher or lower voltages made it the perfect candidate for sending electricity over long distances with minimal power loss.
So it's more efficient to transport electricity over long distances using AC.
Exactly. That's why our power grids are largely based on AC systems, making it possible to deliver electricity to your home even if you live hundreds of miles away from the power plant.
Fascinating. It's amazing to think that these fundamental choices made over a century ago still shape how we power our world today. But beyond just how it's delivered, how does electric current actually work in practice? What can it do?
Well, one of the most basic and useful properties of electric current is its ability to generate heat. Remember those tiny particles flowing through the wire? Well, as they bump and jostle their way through the material, they create friction. And that friction generates heat.
So that's what's happening when I toast my bread in the morning. Or when an old school incandescent light bulb lights up. It's all just these tiny particles creating a microscopic dance party in the wires.
Exactly. We call this phenomenon resistive heating. And it's the principle behind a wide range of everyday appliances, from your hairdryer to your electric stove.
Incredible to think that something so fundamental to our lives is happening at such a tiny scale. But, speaking of tiny scales, I've always been curious about how electricity and magnetism seem to be so intertwined.
Excellent observation. You've stumbled upon one of the most fundamental forces of the universe, a force we call electromagnetism. It's like electricity and magnetism are two sides of the same coin. Whenever electric charges are in motion, they create magnetic fields around them.
Wait, so just by having those tiny particles flowing through a wire, we're creating invisible magnetic fields around them. It's like a secret superpower hidden within electricity.
Precisely. And this superpower is harnessed in countless technologies. Think about those giant electromagnets used to lift cars in junkyards, or the powerful magnets that drive electric motors and everything from your washing machine to electric vehicles. They're all powered by this amazing interaction between electricity and magnetism.
Mind-blowing. It's like a whole new level of understanding how the world works. It's not just about flipping a switch and magically having light. There's this intricate dance of charged particles creating heat magnetic fields and powering our lives.
It really is a beautiful dance, isn't it? And we're just beginning to understand its full potential.
This is already so much more than I ever imagined. But I have a feeling the rabbit hole goes even deeper, doesn't it? Tell me what lies ahead in this grand adventure of electric current.
Well, hold on to your hats, because in the final part of our journey, we'll explore why understanding electric current isn't just about knowing how our gadgets work. It's about unlocking the secrets of nature itself and shaping the future of technology. Don't go anywhere.
Welcome back, everyone. We've been on quite the electrifying journey, exploring the ins and outs of electric current.
Yeah, we've seen how these tiny charged particles, whether they're electrons or ions, create this incredible flow of energy that powers our world.
And we've learned that electric current isn't just one thing. It has different personalities, DC and AC, each with its own story and unique way of moving. But now I want to kind of take a step back and ask the big so what question. Why does all of this matter? Why should we care so much about understanding electric current?
Well, at the most basic level, electric current is like the lifeblood of modern civilization. Our homes, our cities, our communication networks, everything relies on this steady flow of electrons.
Yeah, it's true. It's so easy to take electricity for granted until you experience a power outage. Suddenly we're back in the dark ages. No internet, no lights, no refrigeration. It's a stark reminder of how deeply we depend on this invisible force.
Exactly. But what's even more fascinating is that electric current isn't just a human invention. It's woven into the very fabric of the natural world.
Now that you mention it, I've always been awestruck by lightning. It's such a raw and powerful display of nature's energy.
And guess what? Lightning is essentially a massive surge of electric current. It's nature's own spectacular light show demonstrating the immense power of these charged particles in motion.
Whoa, so even the weather is driven by electric current. I'm starting to see that this is much bigger than just understanding how our gadgets work.
It absolutely is. And if we zoom in even further to the level of our own bodies, we find that electric current plays a vital role there too. Our nervous system, that intricate network that allows us to think and feel and move, relies on tiny electrical impulses constantly zipping back and forth between our brains and every part of our bodies.
You're telling me that my thoughts, my sensations, even my ability to move, are all thanks to these tiny currents flowing through me. It's like we're all walking electrical circuits.
In a way, we are. And the more we learn about electric current, the more we uncover its incredible potential, both in understanding the universe and in shaping the future of technology.
Okay, I'm all ears. What are some of the frontiers where the science of electric current is leading us?
Well, one area that's particularly exciting is the field of superconductivity. You see, at extremely low temperatures, certain materials can conduct electricity with absolutely zero resistance.
Wait, zero resistance? So the electrons are flowing through the material with no energy loss? That's incredible.
It is. It's like having a superhighway for electrons, where they can travel at lightning speeds without encountering any traffic jams.
What kind of implications could this have for technology? I can only imagine it would be revolutionary.
The possibilities are mind-boggling. Imagine power grids that can transmit electricity across vast distances with no energy loss, super efficient computers that operate at lightning speed, and even high-speed levitating trains that glide effortlessly above the tracks.
That sounds like something straight out of science fiction. But you're saying this could actually become reality.
Scientists are making incredible progress in understanding and harnessing superconductivity. It's a field that holds immense promise for the future.
This is truly amazing. Are there any other frontiers in the world of electric current that you're particularly excited about?
Absolutely. Another area that's revolutionizing our world is the realm of semiconductors. These are materials that can control the flow of electricity in very precise ways, acting as gatekeepers that can either allow or block the passage of electrons.
Gatekeepers of electrons. I've heard of semiconductors, of course. Aren't they the brains behind all our digital devices?
You got it. Semiconductors are the building blocks of computer chips, the heart and soul of our smartphones, laptops, and pretty much every electronic gadget we rely on.
So basically, without our understanding of electric current and how to manipulate it at the microscopic level, our digital age simply wouldn't exist.
That's a great way to put it. The ability to control the flow of electrons with such precision has unlocked a universe of possibilities. And as we continue to delve deeper into the mysteries of electric current, who knows what incredible innovations lie ahead?
Well, this has been a truly eye-opening conversation. We've covered so much ground, from the basic principles of electric current to its incredible potential to shape the future. I hope you all found it as fascinating as I have.
It's been a pleasure sharing this journey with you all. We'd love to hear your thoughts on what we've discussed today.
What were some of your biggest takeaways? What questions are still swirling around in your minds? Leave a comment below and let's keep the conversation going.
And if you enjoyed this exploration of electric current, don't forget to hit that subscribe button and ring the notification bell so you don't miss out on future videos exploring the amazing world of science and technology.
Thanks for joining us, everyone. Until next time, stay curious, keep exploring, and never stop asking why.